Hello and welcome to another video. In this video we're going to be going over the problems from Weekly Contest 399, and let's get into it. So in the first problem you have two arrays, nums1 and nums2, and a k, and you want to return the total number of good pairs, where a pair means that you took a number in nums2, you multiplied it by k, and a number in nums1 can divide it. So they show you the example. So for example, since k is 1 here, all of these multiplied by k will just be 1, 3, 4. And so some of the pairs would be like 1 divided by 1 would work, 3 divided by 3, or 4 divided by 1, or 4 divided by 4. And all the numbers can be divided by 1. So what I mean by divided is when you divide them, the remainder has to be 0. So they show you all the ones. In the second example, when you multiply these second numbers by k, this becomes a 6 and this becomes a 12. So the pairs you can have is 12 and 6, and 12 and 12. So you'll have two pairs. So it's pretty easy. You can just kind of like brute force. You just check every single number in nums1, every single number in nums2. If there's a remainder 0, let's add 1. And that's like the solution to the easy problem, and we'll get into an optimized solution in the future one. So this works. Okay, so let's take a look at the next one. So here, this is also kind of an easy one, I think, for a medium problem. Basically, they tell you you have a word, compress it to do the following algorithm. Begin with the empty word. When the word's not empty, use the following operation. Remove a maximum length of prefix made up of a single character of C, repeating at most 9 times. Append the length of the prefix followed by C and return it. So for A, B, C, D, E, you would basically just get 1A, then 1B, then 1C, then 1D, then 1E, which would give you one of each. And then for this, so there are 14 A's, I believe. Let's see, 2, 4, 6. Yeah, I'm just going to assume because of this. So there's 14 A's. So you can only get a chunk of 9 at a time. So you'd get 2, 4, 6, 8, 9. And then you would say, okay, we have 9 here. Then you'd start over here, and you'd get 5 more. And you'd say, okay, we have 5 more, and then 2 B's. So it's pretty easy. You just start at a character, and you keep going while the character is the same, and while the count of the character is less than 9. So for example, if we start here, we'll say, like, okay, while the next character is the same as the first one, and we have 9 or less, let's keep going. So we're going to get 9 here. And then when we get 9, we're done, and then we'll start at the next character. So when we get 9, we'll just take the number of however many we had, or if we had less than 9, we'll take that number, and we're going to append to our result the number that we have and the character. And something a little bit good for efficiency is if you're building a big string. So like, let's say worst case scenario, this string is just like alternating characters like this. So if you were doing this and you were building, then you would have like 1A, 1B, 1A, 1B. And when you do this to a huge string, that's not going to be super good. So instead, you can make an array. So you can just store like 1A, 1B, 1C, or 1A. And then that way, when you add one more character, it's cheap. And then you just combine the whole thing at the end. So pretty straightforward. Just go through the thing, get up to 9 of the same character, and then append the number that you have and the character and return it joined. Like I said, this will be a lot worse if you just were to manually keep adding this to a string. Okay, so this one, the third one, is basically the first problem, just can you do it more efficiently, because the constraints are 10 to the 5th, so you can't have the n-squared solution. And there's kind of two ways to do this, and I'll talk about some optimization. So for one thing, so in order for a number in nums1 to be divisible by, so let's say we have some number. In order for this to be true, right, in order for this to be true, that means that this has to be true. So the number has to be, k has to be a factor of the number. So for like 1, that doesn't really help us much because 1 will be a factor of all of these. But if k is like 3, none of these numbers can be used to make a good pair if they're not divisible by k. Because how could like 4 be divisible by 3 times something if 4 is not divisible by 3? That wouldn't make any sense. So what you can say is for every number in nums1, if it's not divisible by k, just throw those out. So like for the second example, you would just have only 12. And so this, obviously worst case, if k is 1, it's still not going to help that much, but that's like a slight optimization. Then the next thing we can do is we can actually, so because we're going to be doing, either way you have to do factors, we can do another optimization where we can say, okay, well we're trying to do num1, is it divisible by num2 times k? Well, if that's the case, why can't we just divide the first number by k and then see if it's divisible by num2, right? Because if we're checking like if x is divisible by y times k, well, we can just divide x by y, or divide x by k, and just check, is that divisible by y now? And that's the same thing. So is this divisible by y? And so that's what you can do. So first you can check if every number in nums1, is it divisible by k? If it's not, throw all those out. Then divide them all by k, which will make your number smaller. Then there's kind of two ways to solve it. A, you can get all the factors of nums1. So for every single number, you get all of its factors, and you can do this in square root time. And this is like a prime factorization, so I can link my prime factorization video. But the basic idea is, if we have a number, if all the factors of the number, like you'll have pairs of factors, right? So for a number, let's say you call it like j, you'll have pairs of factors. So it'll be like x times y, right? And one of these factors has to be, for every pair of factors, one of the factors has to be less than or equal to the square root of j. And that's because, let's just think of like a big number like 36. So the factors that are closest to each other in 36 is 6 by 6. And so if we increase one of them, the other one has to decrease, right? For like every number that's a perfect square, like 25 or 36 or whatever, there's going to be two factors that are exactly the same. And if we increase one, in order for these still to match up, like let's say I make this 9, this has to be less. So that means that one of the factors is guaranteed to be less than or equal to the square root of the number. So basically, one way to do it is you get all the factors of nums1, and you can get those in square root of time. So you just go through every single number, you get all the factors, and you check, is each one of those pairs of factors in here? And if it is, let me increase that. And the other optimization is, so here there's no duplicates, but if there's duplicates, like let's say nums2 is like 1, 1, 1, 1, 1. We don't want to see like how many, like we don't want to have this like this. Instead, what we want to have is a dictionary. So we can have like 1 with a count of 8. That way, when we reach a factor of 1 with a count of 8, we'll say like, oh, we found a 1, it was a factor, how many times does it appear? So that's more efficient as well. You can probably do this in nums1 as well. You can probably make them both a dictionary. That would probably make it a little bit better as well. But I didn't do that. So it's basically, you can turn nums2 into a dictionary of the number and the count. And then for every number, you just go through factors. So for example, after we divide our 12 by 3, we'll get 4. And then we'll say like, okay, well for 4, what are the factors? So 4 factors 1, is 1 in here? No. 2 is also a factor. Is 2 in here? Yes. So that's one thing. And then also 4 is a factor. So that's another one. So that's how we have 2. That's one way. Another way you could solve this problem is you can kind of do it the other way, where what we can do is for every single number in nums2, first turn it into a dictionary. Because imagine in worst case, every single number in nums1 would be like pretty big and probably different. So let's say it's like 1, 2, 3, 4, 5, 6, so on, right? Or just some really big numbers. Actually, it wouldn't even be this. It would be like, because these numbers can get really big, let's say it's like 10 to the 5th, 10 to the 5th plus 1, and so on and so on and so on and so on. And this whole thing ends up being 10 to the 5th size. So every single one of these is unique, and also every single number in nums2 is like 1, or let's say we have this case. Like this would be a terrible case if you didn't use a dictionary. Because if you didn't use a dictionary, what we're going to do is for every single number in nums2, and let's say k is 1, that would also be the worst case. Because then every single number in nums1 would be divisible by every single number in nums2. So if this is the case, if you don't use a dictionary, what we're going to do is for every single number in nums2, we're going to take its multiples up to the biggest number in nums1. And if this was the case, we'd basically have to say like, okay, let's get all these multiples up to the biggest number, and that would take about, let's say the biggest number here is 10 to the 6th, that would be about 10 to the 6th, and then for this one it would be 10 to the 6th, and this one would be 10 to the 6th, and so on and so on. So that would be pretty bad. So instead, that's why you want to combine these into a dictionary, because if you have something like this, then basically worst case for the number 1 and this condition, this will take 10 to the 6th time, because essentially you're gonna like get you're gonna get all the multiples of 1 that can be up to this number, which will be like 1, 2, 3, 4, 5, 6, so on, so on, so on. So that would be 10 to the 6th. But now you're only gonna have unique numbers. So maybe you'll have like 1, then you'll have 2. So from 2 to 10 to the 6th, that takes, so 1 takes time n, where n is like the biggest number in the first array. 2 takes time n over 2, right? Because you do like 2, 4, 6, 8, and so on. 3 would take time n over 3, and so on and so on and so on. So you'd basically get this thing where you get like n plus n over 2 plus n over 3 plus n over 4 plus n over 5 up until n over, let's call it like 10 to the 5th or something. And I think the sum of this ends up being like n log n. So what we can do is for every single number in nums2, we can just take all of its multiples and put them in an array. So what we're going to do is we're going to make an array of we're going to make an array of counts of all the multiples of nums2. So essentially, let's say nums1 had numbers like 1, 2, 3, and then maybe like 10 to the fifth or something. And we did the whole divide by decay, we did all that. So essentially, we're going to make an array that's going to be length 10 to the fifth. And it's all going to have 0. So it'll be 0, 0, 0, 0, 0, 0, 0, 0, 0. Up until length 10 to the fifth. And then for every single number in nums2, we can just get all the multiples of it. And then every time we get a multiple, we'll update the count in this frequency array. So at the end, this frequency array will basically have every single multiple that we got and the count of it. And then it's pretty easy. All we have to do is go through every number in nums1 and just check how many times did that number appear in our multiples array. So let's kind of walk through that example really quick. So let's say our numbers in nums1 where it doesn't really matter what they are. Let's say there's like 1, 2, 5, 10. And the numbers in nums2 were like 2, or let's say maybe this is like 1, 2, 5, 10. Let's not do 10. Let's do 10. Let's do like 40. And then in nums2, maybe we had like, we're not going to use 1 because it's going to take too long. Like we don't want to do that. So let's say we have like 3, 5, 6 or something. So basically we do all the k stuff. Let's pretend that these actually matched. And let's say k is like 1. So what we're going to say is, okay, so we're going to have an array of 40 multiples and their counts. So I'm just going to write out the multiples that we have, but instead these will be an array. So for 3, we can get like 3, 6, 9, 12, 15, 18, 21, 24, 27, 30, 33, 36, 39. So these would be all the multiples that are in the range of 1 to the biggest number in here, because anything bigger than this doesn't matter. Then we do the same thing for 5. So for 5, we're going to get 5, 10, 15, 20, 25, 30, 35, 40. And for 6, same thing. So 6, 12, 18, 24, 30, 36. And then basically, so instead of actually storing these numbers in an array, we'll take our multiples array that we have and we'll update all of these indices to be one more number. Actually, not one more number, but the number of times that this number occurs, right? Because let's say in our nums2, 3 actually occurs 8 times, 5 occurs 10 times, 6 occurs 10 times. So that way we only have to do this for every unique number. So instead of like 1 3 in here, we'll have 8 3s and 8 6s and so on and so on and so on. So that's the basic idea, is you go through all, so let's just walk through the code actually. So first, we're going to take every single number in nums1, and if it's not divisible by k, we can throw it out immediately because that will never be a good number. Then if we have no numbers in here, we can just return because that's no good. Then we're going to get a count of every number in nums2. We're going to get the biggest number in nums1, and we're going to make this array of the counts of every single multiple of nums2 that's going to be length the biggest number in nums1. Then we're going to go through every single number in the dictionary of the nums2 numbers. So it's going to be a number and a count. And we're just going to loop. So we're going to start at that number and we're going to loop from that number up until the biggest number we have. So let's say our biggest number is 40 and our current number is 2. We'll have like 2, 4, 6, 8, and so on. And we'll increase by that number. And we're going to take the array at that index, and whenever we reach it, we'll just add the count of the current number we're on. Then all we have to do is just go through every number in our new array that we made and check how many times that occur in the multiples and return it. So there we go. Okay, so that's that one. And now the last one. And the last one is extremely hard. So I will say you have to know how to do segment trees. So I do have a video on segment trees, and I basically copy pasted my segment tree template, and then I modified that. So essentially what this, I'll talk about like kind of, I think I actually have it here. Essentially, you're given an array of nums consisting of integers. You're also given queries or queries position. And the basic idea here is you have some array. So I actually have an example, I think. Maybe I don't. Okay, so let's just make some numbers up. So let's just say we have some array like this. And this array is going to have some numbers. So maybe like this is this, 4, 8, 1, 5, whatever. Something like this. And you basically have this. And for every query, you're going to change one of these numbers, And then they want you to basically, this is literally, they basically want you to do a house robber problem on this. So you can pick any elements from here as long as no two adjacent elements are picked. So like in this case, let's maybe make this smaller because then it would make it easier to figure out like what's the best solution. So maybe let's just cut it down to here. So like in this case, obviously the best solution would be picking the 8 and then the 3, right? So that would be the best case. Now if we go back to this bigger thing, who knows? Actually, I think it's pretty straightforward. So it's going to be like pick the 9, pick the 8, pick the 3, pick the 5. That would give you the best. Right? So basic house robber, but your basic problem is, okay, well you have 5 times 10 to the 4th numbers, and for every query, you're basically saying, okay, I'm going to change one of these numbers, and now give me this solution again. And so if you know for house robber, the optimal solution is O of n. So if you were to do that, if you were to just do a DP, like change a number to a DP, this would give you n times q, and that would fail. I think it actually passed for some languages, but it's supposed to fail. So you need to do something better. And the way to do something better, and this is not obvious at all, is basically you need to say, okay, how do I change these numbers, but then like save some information that I had before, and then, you know, give you this result better. And the way to do it is actually with a segment tree. And so let's go through an example of, first of all, like the basic thing you're trying to do with a segment tree is given two ranges, how do I combine them to give me a result? And if I can do that, then I can recursively do that. So you do have to know how a segment tree works, but let's say like we have these two ranges. And now I want to say like, okay, I have these two ranges and maybe I know like the best number in here and the best number in here. So what do I need to get like the best number in the whole thing? Well, let's say the best number in here is 11 and the best number in here is 14. And so there's a couple possibilities here, right? Because you know for sure, like basically if you could solve how do I combine these two into one whole range? Let's see here. How do I combine these two into one whole range like this? And if you can do that, then you basically solve the problem because you can just do this recursively and build your whole tree. And if you know a segment tree is logarithmic. So let's bring this down here. So you're basically saying, how do I combine these two? So this would be the range from 0 to 3, and this would be the range from 4 to 7. And if you can do that, then you can keep doing that, and you can keep doing that, and then you can just query your root node, and that would give you your answer. But what information do I need? Well, I can combine this in a couple different ways. So what information do I need to know here? And also, if I need to know some information in these to calculate this, then I need to have some information in this to maybe it has more nodes, like maybe this isn't the root, maybe there's like some other stuff up here. So any information I need in this to calculate this, I also need in this as well. And you're trying to figure out like what's the minimal amount of stuff. So when you combine these two things, there's a couple possibilities. There's basically two. One, you could say, okay, maybe I know what's the best in this, but in order to combine these, I can't just combine them, because what if in this node, the best solution, let's actually change this a little bit. So let's put the 9 here. And let's put the 2 and the 5. So like this. So to make more sense. So here, this is 11. Like, yeah, like we can say, like, we can take these two. And here, we can take these two. But the problem is when we combine them, we actually can't use these because they're together. So you basically have one of two ways to get, like, the best total here. Either left minus its rightmost node, or, and this is going to be combined with right, the full right array, or left, the full left array, and right minus leftmost node. And what I mean here is we can either say, okay, we'll just not use this node, and then we can use this whole thing, whatever the best result is in this whole thing, or we can not use this thing, and then we can use this. So you need this information. So we need this like left minus rightmost node, and we need right minus leftmost node. And if we have that, then we can calculate it. So let's see how we would get that. And think about like for this was calculated from some other recursive part where, you know, there was like some section here, some section here. So if you can't, like, you actually have to calculate this as well, because like I said, for this thing you might need to use this later. So for this thing we need to know like the overall best, and we need to know here these two things, right? So we need to basically have this left, we need to have the missing the leftmost node and missing the rightmost node, essentially, right? Because you never know how you're going to combine things. So like in this case, we have to try to combine maybe like this, maybe like this, you know, we might have to combine this with something else, maybe like this, and so on and so on and so on. So there's two more things that you need to know, right? So the overall best, which is like what's the whole best thing, then missing leftmost node, and then missing rightmost node. But the problem is, to calculate these two, to calculate missing the leftmost node and missing the rightmost node, there's kind of two possibilities. Like let's think about if we calculate this, missing the rightmost node, how could we have gotten here? Like let's say we're trying to calculate this. Well, we could have gotten here a few different ways, right? We can either, so we know for sure that the right side, like if these recurse up to here, we know for sure this right side has to be missing, right? Like that's for sure. But there's still a couple of cases here. We can still have two cases. We can have this case where this node is not used and this node is, and like this whole tree is available. Or we can have this case. And so you see how this case is brand new. This is one we didn't talk about, and this is missing both the left and the rightmost node. And similarly, if we were trying to calculate missing the leftmost node, so this for sure has to be missing. But you can have two cases as well here, right? You can have this case where this is missing and this is fine, which is missing the left and right. Or you can have this, which is this is missing the left and this is missing the left. So essentially there's one more case you need to keep track of, and with these four, you'll have everything you need. So you can have missing the leftmost, missing the rightmost, overall using the whole thing, or missing left and rightmost nodes. So that's essentially the idea, is we can build a segment tree with this information, and then when we update, we will update a node, and for the parent, we can calculate this using the children. So let's kind of do this using a really small tree, because this gets kind of annoying. And I'll actually show the code and it'll make a lot of sense. So I'm going to reference the code here and actually did this right here. So no left or right means missing the left and rightmost node. This is missing left, this is missing right, and this is having everything. And I have these indices so we can actually reference this. So maybe I'll actually copy it here and we can reference this in the tree, and then we can compare a solution. So let's maybe put it here. Okay, so now we're going to build a tree, and with the root nodes, we'll have like an actual thing. So let's just have a tree that's not too big. Maybe like this. It's kind of big, but not that bad. Okay, so for the basically this is what we're going to have for every single node. So essentially we're going to have an array of 4 values, right? So this no left or right means missing both left and right, missing the left, missing the right, and missing both. So for the root nodes, if you think about it, you're only going to have like one element, right? Like for a segment tree, this represents one index, so it'll be like 0 to 0, which means if you're missing the left or the right, you're missing both, you basically don't have anything. Because you can't, if you only have one node, if you're missing the left but you have the right, like you're missing the left, so you shouldn't have anything. So the only value that will be true will be this, and that will just be equal to the value of the node. So let's just put in some values here from here, like 1, 3, 4, 8, 9, 2, 5, 1. So 4, 8, 9, 2, 5, 1. And then what we're going to do is we're going to delete these things, because this will actually be arrays of these 4 elements. So let's kind of walk through what this should be now. So for this parent, so this is missing the left and the right. So obviously these both shouldn't be there, so there should just be 0. And if you look, it's the maximum of the left. Oh, well, I guess, yeah, we'll just write it 0. I'm not going to go through the computation. This will just be, basically, if you do this exact thing, for the child, it will be 0. So for the child, for each child, it looks like this. So it'll be like 0, 0, 0, and then the value of the node. because the only one that's valid is not missing anything. So in here, missing the left and the right will just be 0. Okay, there we go. Now missing the left means we only have the right, so that'll just be 2. Missing the right means we only have the left, so that'll be 1. And then when you have both, what's going to be better? It's just going to be the biggest value, so that'll just be 2. So let's do the same thing for this. So missing both will be 0. Missing the left will be the right value. Missing the right will be the left value. And having both will just be the bigger value. Then same thing here. So missing the left will be 2. Missing the right will be 9. And having the bigger will be this. And here. So missing the left will be 1. Missing the right will be 5. Bigger is 5. Okay, now let's do these for the, so there's 3 more. So now we actually do need to figure out like, and instead of using the equation, we're just going to think about like what's actually best. So here, this means we're missing the left and the rightmost node. So both of these are missing. So what's better here? We can only pick one. It's just going to be the 4, right? Okay, now we're missing the left. So what's the best thing here? Well, the best thing here is going to be the 8 and the 2. So 10. Then missing the right, we're missing this. So what's going to be the best here? It's going to be the 4 and the 1, so 5. Hopefully I calculate this correct. And like I said, if you actually use this equation, it should give you the same thing. And now this is just the full path. So what's best in the full path? This is just 8 and 2, so 10. Okay, and same thing over here. So missing the left and the right means we're missing the 9 and the 1, so it's just the bigger of the 5 and the 2, so 5. Missing the left means we're missing the 9, so that's just 5. Missing the right means we're missing the 1, so 5 and 9, so 14. And the whole thing will be 14. So obviously the whole thing should always be bigger than like missing some stuff, so you can double check that. And finally, the whole path. So let's take a look. So missing both the left and the right, the best path. We can use the equation, I guess, if we want to. So I guess let's use the equation here. So missing the left and the right means you're taking left vals 1, which is this value here, and right vals 0, which is 5. So we should get 15. We'll double check these. So this should be this, I think. Actually, no. I think I did that wrong. So left vals 1, which is 10. Oh yeah. So this part right here is the first one, and then the second one we have to try is left vals 0 and right vals 2. So left vals 0 is 4, right vals 2 is 14. So it's actually going to be 18. So that's the best missing this. So let's just double check that really quick. So if we are missing these 2 values, we should be able to get a path of length 18 if we did everything correctly. So I think it's probably like this. 9, 5, 4 is our path, right? Yeah, so that's 18. Okay. So we did that correctly. So now I'm missing the left. So if we're missing the left, 9, 5, 4 should still be the best path. So it should still be 18, but let's double check. So left vals 1, right vals 1, which is 15, or left vals 0, right vals 3, which is 18. Okay. Now missing the right should still be the same thing. So it should still be 18 because we're just missing this node here and we still have everything. Yeah, so let's just double check that. So that's this one over here. So left vals 3, right vals 0. So 3, 0 is 15. And then left vals 2, right vals 2. So it's actually 19. So let's double check. So if we're missing this value here, can we get 19? So we get this. Yeah, 19. Okay. And finally, for the last one, what's the best path? Let's plug that in again. So it should be 3 and 1, so 10 and 5, which is 15, or 2 and 3, which is 19. So yeah, I think 19 is the best because we want this guy, this guy, this guy, and this guy. So that's kind of the idea is, let me look at the code now. So the basic code is, so this segment tree is copy pasted from my segment tree video. So I'll link that. You can probably write it cleaner. I just copy pasted it because it had like good comments and stuff. And let me quickly go over what I changed in the segment tree. So essentially, for the values of the segment tree, like I said, this is missing both the left and the right. This is missing the left, missing the right, and then missing both. And that's what I wrote right here. So essentially, that's what you have. So for the value in every single node, you have these 4 values. Then you make the tree, and then to actually calculate the value of the tree from the roots, or from the children, it's these conditions, right? So this is another good one. If you either done a segment tree or you haven't, start with like building it and then make sure these things are correct. Walk through this picture and make sure all your stuff is correct, because it doesn't make a lot of sense. Like once you think about it, like if I have these arrays, how do I combine them? Like if I'm, if I combine two arrays, I can either delete this, or like if I have to not have this element, what does it look like, and so on. So you can walk through it and make sure that it all makes sense. So you calculate all these values for the node based on its children, and then you just return that. Then the nice thing is for an update. So for an update, the code is very similar. So all we do is just, and this is why an update is fast. So when we query, all we're going to query is we're just going to query this root. We're going to query the root when we're not missing anything, because that's going to be like, that's always going to be the answer. So the query will be an O of 1, because normally in a query, you have to do like a range query, but in this case, our query is always the entire array, right? Like what's the best in the whole thing. So we don't have to, so the query isn't going to be logarithmic, but if we update a value, basically we're going to say like, okay, let's branch down some way. Maybe we'll update this value to 10, let's say. So yeah, let's say we update this to 10. Then what would happen here is we would update this guy. Then we would come up here and we would update this guy, and then we would update this. So it's basically, you can think about it is like you have a perfectly balanced tree and you're updating one child and then recursing up to the parent. So it's logarithmic because you're not going through all the nodes. You're only going down one path and then recursing back up, which is logarithmic, because you're basically going down the height of the tree, right? And in a balanced tree, height of the tree is log n. And so that's why this works, is every query will take log n now, and the actual getting the number will be O of 1. So in the actual querying, I think I actually deleted it completely because we basically don't need a query function anymore. So it's pretty straightforward now. Now there are some, I think you update some stuff to negative, and so that'll give you negative solution, but you have the choice to just not take anything. So what I did there is if I got a negative solution, I just said just return 0, because it would be better not to take anything. You could also update all of these to be max of all these things and 0 if you want to. That would also work. So you could put like this 0 and so on to all of these and all of these. But the rest of it is really easy. The actual code, after you build the segment tree, you just basically go through all the queries, you update the index to the number they have, and then you just check, is the number positive? If it is, let me get that. And so this is the value you're going to be using all the time. It's going to be the root with nothing missing, right? Because like I said before, if you scroll up here, there's going to be no left or right, no left, no right, and both left and right. And for the root, you are allowed to include every node in the tree. So yeah, it's definitely a very hard problem, very hard to figure out when like you even need a segment tree. And then once you figure out that you need a segment tree, it's also not it's also not easy to like, okay, how do I build a segment tree? Like maybe I know how to build a basic segment tree where I'm just doing like a range sum query or range max query. Well, how do I do that for this house robber thing? Definitely not easy. And so this is definitely like an 8 or 7. I think it's like an 8-point problem, and definitely makes a lot of sense why it's like that. And yeah, so this should be working. There we go. And yeah, so I will link my segment tree video. If you haven't seen that, you can watch that and like figure out how a segment tree works. This is basically not solvable without a segment tree. Like it is solvable without a segment tree, but if you don't know how a segment tree works, I'd recommend trying that for some basic queries first and then do this problem. Yeah, so let's go through the time and space for all these. So essentially here now, so for the time, so for every single, like to build the segment tree takes O of n. And then to make a query is log n. So it's going to be like n plus q log n. Yeah, I think it's going to be all there on the space. So the way I built the segment tree is also, I think it's probably more efficient to build it in an array, but I built it with an actual tree, which makes it easier to build, but maybe slower. But the time and space and all that's going to be the same. They're just more overhead. So essentially, the segment tree, every node is going to be n. So I think what ends up happening is if you have like an array of length n, like let's say you have 8, then the bottom level will be 8, and then the level above that will be 4, and then 2, and then 1, and so on. So it'll basically be O of n space, right? And then the Yeah, I think you're basically just using the segment tree, nothing else. And then every segment tree has 4 values, which is like O of 1 and all that stuff. So I think it's just this. Okay, let's go to the previous one. So for this one, so you're building a new array for nums1, so that's already nums1. You're building a counter for nums2, so that's like nums2 because they could all be unique. Or I guess that's not in the O complexity. So you are doing all these things. Also, for every single number in nums2, you are getting all of its multiples, which is like, I think this becomes altogether like nums2 log nums2 as like getting all that. So it's something like this, and then for the space, like I said, you're building a counter and you're building a new nums1 array. So it's something like this. Yeah. Okay, and yeah. The string compression guy is just, so you have to build a result, but that doesn't count, and then you have to go through the string such as O of n space like O of 1, I think, because you're just building the result and that's all you're using. And this guy is just O of n squared and O1 space. Yeah, hopefully this is helpful. Definitely a hard contest. And the other one I haven't finished yet that also has a segment tree, and I think it's even harder. So that's going to take me some time. I did the first 3 problems. They're pretty easy. But once I finish that one, I'll make the video for that for the bi-weekly one. So thanks for watching, and I'll see you in the next one.